Hi folks, I was asked to make another video and kind of explain a little bit more some examples with the derivatives of trig functions. So first off, I want to kind of do what I did in the other video with the exponential functions and just look at why the derivatives of trig functions, like how they make sense graphically. So up here I've got a really rough, like no scale or anything, but a sketch of the regular y equals sine x function. Now, if I wanted to see what the derivative of this function was at certain points, one of the most common points to look at would be the turning points. So these max min, remember the derivative is the slope of the tangent. That's so important. So the derivative here is the slope of the tangent, and these would have horizontal tangents or a slope of 0 at those points. So I'm going to graph where my derivative would be just on the same grid. And we see that from here, if we look at the first quadrant piece, I don't know if you guys remember, I know my class last semester for advanced functions, and I had a bunch of you guys in there, we looked at what was the IRC at these points, at the intercepts of the regular sine and cos trig functions. So we actually just calculated with the like 0.01 as our delta x and estimated what was the IRC at those points. And we found that the IRC, which is actually the derivative, here was a +1. Now that's only true if you're measuring in radians. If you're measuring in degrees, then you can kind of imagine the scale of your graph is way off because you're going like up to 1 and down to -1, but the scale would go all the way to like 360 for a full cycle. So the scale there is much, much different. If we use a scale in radians though, we're going up to 1, down to -1, and this is 2 pi, which is about 6.28. So that gives us a much more kind of accurate scale. If we're measuring in the x and y direction, it's about the same scale that gives us this nice slope of 1. So I'm going to put a point at 1 up there. And we see that the slope of the tangent is 1. That's as big as it gets. It like levels off and gets to be smaller and smaller positives. So this starts at 1 and it goes smaller and smaller positives until it gets to this slope of 0 at the turning point. And same thing here. Now the slope, if I'm looking in this second quadrant piece of the sine function, the slope is going negative. It's going to hit a maximum, or I guess a minimum negative slope of -1 at the intercept. So it starts off small negatives and gets steeper negatives. So it's going to go down and hit a maximum negative slope or a minimum slope of -1. Then it's going to start increasing, going into smaller negative numbers back up to 0. And you guys can see, I think what's happening up here, you're going to have a slope of 1 again because this is going to repeat. So it's going to go up and have a maximum slope of 1. And hopefully what you see here is that from my original function, f at x equals sine x, that if we kind of sketch out where the derivative values would be, we see another important function, and that is that f prime at x equals cos x. Now you can do the same thing for the graph of cosine and sketch that out and see what the derivative function would look like. Everybody always wants it to be sine because wouldn't that be cool, but it's actually negative sine just because of how it's shifted. So we know, and I've posted up a summary here, we know that if f at x equals sine x, f prime at x equals cos x. And if f at x equals cos x, f prime at x equals negative sine x. The other derivative rule that you guys are going to have to know is that if f at x equals tan x, f prime at x equals secant squared x. And that's a bit more complicated proof to do, but we will look at that in Unit 5. Now I wanted to do some examples of applying these derivatives because this is pretty straightforward, but having a function that's just sine x or just cos x is pretty boring and you're not really doing much with it. If there's something else, so if it's not just a sine x, if it's a sine of something else, like in this example, you're going to do the derivative the same way. So you keep the angle measurement the same, and the derivative will be the cosine function, but we'll have to multiply that by the derivative of the angle. So for this example, I'm got f at x equals sine of x squared plus 3x, and then minus the cosine of root x. So some people have a hard time, for sure, I think it's pretty normal to have a hard time doing derivative of a square root. So make sure you're thinking of that as x to the 1/2. I always think of that in exponential form. And you can rewrite that just as a whole separate line to rewrite it to be ready to do the derivative if you want. So I'm going to do the derivative here. So f prime at x equals, so I'm going to color code things a little bit. This stuff in here is the angle of my first function. So the derivative of sine is cos. So I'm going to have the derivative for f prime at x is cos of this same stuff. So of x squared plus 3x. But that's not the only piece of this derivative. We also have to, so we're keeping this the same, but then we have to multiply by the derivative of that pink boxed function that was in my original sine function. So I have to multiply this by the derivative of this inside stuff. So that inside stuff is x squared plus 3x. The derivative of that is 2x plus 3. And you can see that this is a little ambiguous with how it's written with cos of one thing in brackets, but then another bracket. I'm always going to want you guys to rewrite that coefficient. I always put it here because that's kind of the order of doing the derivative, but I'm going to pull that out front just to make it really clear that this 2x plus 3 is not part of the angle, it's the coefficient of my cosine. So I'm just kind of pulling it out front. And I probably should have finished this first, but we'll keep going. So then the next piece of this is doing the derivative of cos of root x. So we know that the derivative of cos is negative sine, and I already have a negative, so that's going to make this positive sine, and you can write x to the 1/2 or root x, it doesn't matter. So I'm keeping this the same. So if I kind of say this stuff here stays the same. So this is kind of like the pink box derivative. So I'm putting kind of pink box prime there, what I did the derivative of the stuff in the pink box. So I'm keeping the pink box the same in the new cos function, multiply by the derivative. I'm doing the same thing here. Keep the green box stuff the same, and then I have to multiply by the derivative of the stuff in that green box. So that is times 1/2 x to the negative 1/2. The exponent comes down, keep the base the same, and reduce the exponent by 1. So again, this is not actual any kind of math notation, but this is kind of like green box prime. It's the derivative of the green box. Okay? And again, we want to rewrite that in a way that really shows that this is not anything to do with the angle. This is just a multiplier of my sine x function. So I'm going to put plus. I'm going to put sine on the top. The 2 is on the bottom. I'm going to bring down that x to the 1/2 on the denominator here on the bottom of my fraction with the 2. And you could write that as 2x to the 1/2 or 2 root x. So that's how I do the derivative of that function. The next one is pretty tricky. Like these first two terms for sure are pretty tricky to think about. So again, remember the differences in notation. I want you guys to be comfortable using the f prime, the y to going to dy dx or y prime. So my first piece of this function is e to the exponent sine x. So from the exponential functions examples, we know that the derivative of e to the anything is e to that same exponent times the derivative of the exponent. So I'm going to keep this the same, which this looks like a crazy function, but it's going to work kind of the same as what we did. So e to the sine x, I'm keeping that the same, and then I'm going to multiply by the derivative of the pink box. So I'm going to kind of do this like not math, not good thing notation down at the bottom. So now I'm going to multiply by the derivative of sine x, which is cos x. And my next one, I have sine of e to the x. So this is kind of the opposite here. So I know that the derivative of sine is cos of the same thing. So now I'm going to put cos e to the x. So this now is like my green box. So that stays the same in the derivative function. Then you have to multiply by the derivative of the stuff in that green box. So then we're going to multiply by e to the x. Better mute my computer. I'm getting too many emails. The last step is not so bad. The derivative of tan is secant squared. I've got a minus, so I'm going to keep that. And I am running out of colored markers. So I'm going to have this is secant squared, and the same thing, I have to use pencil even though that's kind of boring. So this thing in here is what stays in the derivative function. So this is secant squared of x to the 7, and then I have to multiply by the derivative of the inside stuff. And the derivative here of the inside stuff is not so hard. It's 7x to the 6. Now, always with trig functions, you want to write those at the end because, again, it can be pretty ambivalent or ambiguous, I guess, about what stuff is part of the trig function. So I would rewrite this e to the sine x times cos x. I don't like this e to the x here because it's not super clear that it's not going to accidentally get in to be part of the angle in that trig function. So I'm going to bring this e to the x here out front to make it really clear that it's a coefficient. And same thing with this 7x to the 6, because sometimes people might multiply that together. It's not multiplied by just the angle, it's multiplied by the whole secant squared. So I'm going to bring that out to the front, make it really clear that it is a coefficient, not a piece in the angle argument of that function. I also have done some solutions that people emailed me about that I will be posting up as well. So please, take a look at those. There's some from 256 and some from 260, I think. If there's any other questions that you guys have, post homework questions, I'm happy to help.